The collapse takes less than a second. When the iron core passes about 1 4/10 solar masses, the support gives out, and the middle of the star falls. It falls from something around the size of Earth to something around 20 kilometers across. It does this in well under a second, and the inner part reaches a quarter of the speed of light on the way in. Then it hits itself. The center becomes so dense that it stops being compressible, and the material still falling in bounces off it. That bounce, helped along by everything described in the next fact, drives a shock wave back outwards. Here is the part that is hard to picture. The star is enormous. The shock has to travel from the middle all the way out through hundreds of thousands or millions of kilometers of the star's own body before anything is visible from outside. Depending on the size of the star, that takes hours, sometimes most of a day. For that whole time the star is already destroyed and still looks completely ordinary. The surface is shining exactly as it did the day before. Then the shock arrives, the surface is lifted off, and the object brightens by a factor of billions in a few hours. The delay is not a theory. It was measured in 1987, when a star died in a nearby galaxy, and 2 different kinds of signal arrived from it at 2 different times, which is the subject of the next fact. Almost none of a supernova comes out as light. A supernova is the brightest thing most people have ever heard of. For a few weeks, one star can outshine the entire galaxy it sits in. That display is about 1% of the energy, less in most estimates. The overwhelming majority leaves as neutrinos. When the core collapses, protons and electrons are pressed together into neutrons, and every one of those reactions releases a neutrino. Something like 10 to the 58th of them come out in about 10 seconds. Neutrinos barely interact with anything, so they pass straight out through the entire body of the dying star at nearly the speed of light, while the shock wave is still grinding its way outwards. Which means they arrive first. On the 23rd of February, 1987, 3 detectors in Japan, the United States, and Russia recorded a total of about 24 neutrino events within roughly 13 seconds of each other. Around 3 hours later, astronomers in the southern hemisphere saw a new star in the Large Magellanic Cloud, 168,000 light-years away. 24 particles. That is what a nearby exploding star delivers to instruments the size of a swimming pool, and it was enough to confirm the whole picture of what happens inside. It remains the only supernova whose neutrinos anybody has ever caught. There are detectors on watch for the next one, connected to an alert system, because the neutrinos give a few hours of warning before there is anything to point a telescope at. A spoonful of what is left weighs as much as a mountain. If what remains after the collapse is under about 2 or 3 solar masses, it settles as a neutron star. Take 1.5 times the mass of the Sun, put it in a ball 20 kilometers across, about the size of a city. That is a density comparable to an atomic nucleus, and a teaspoon of it would weigh something like 1 billion tons. The other thing that happens is spin. Anything that shrinks spins up, the same way a skater does by pulling their arms in, and this is a shrink by a factor of tens of thousands. A core turning once a month comes out turning several times a second. The fastest one found so far completes 716 turns per second. That is an object the size of a city, heavier than the Sun, spinning faster than a kitchen blender. Many of them fire a beam out along a magnetic axis, and if that beam sweeps past Earth, we receive a pulse each time it comes round. They are called pulsars, and they are among the steadiest clocks in existence. The first one was found in 1967 by Jocelyn Bell Burnell, who noticed a repeating signal in a chart recording from a radio telescope she had helped build. The signal was so regular that the group half-seriously labeled it LGM-1 for Little Green Men, until a second one turned up in another part of the sky and settled the question. If the leftover is heavier than about 3 solar masses, nothing known stops it, and it goes on collapsing into a black hole. That is a whole subject of its own, and not for tonight.